So, Unit 9, Lesson 11 is called Sampling and Predicting. And I find this to be one of the more interesting units because it's such an application for the real world. When you take a sample of something, it's usually because the population is too big. So, the sample is part of a larger group called the population. Trying to count all the whales in the ocean or all the squirrels in a city park would be rather difficult. So, researchers will take a sample and make a prediction about a population. However, a representative sample must be taken to make a prediction. A representative sample happens when the sample of people or objects accurately represents a smaller picture of everyone or everything in the entire population. Back to estimating the number of animals in a large location. One way to estimate, say, the number of frogs in a large pond is the capture-recapture method. Now, we do this in New Hampshire for moose. We actually have a moose lottery for people that hunt, and they only allow a set number of licenses to be given out. And those are given because people in New Hampshire do this capture-recapture method to find out how many moose we have in the state. So this is really applicable to everyday sort of things happening in our state. A biologist needs to estimate the frog population in a large pond. She captures 75 frogs, tags them, and releases them back into the pond. So we're going to call that the sample, right? She captures 75 frogs, tags them, and releases them back into the pond. 1 week later, she observes that 7 frogs have tags out of the 50 she recaptures. About how many frogs are in the pond? So this is a second statistic, and you'll notice that it has 2 numbers in it because it's going to be its own fraction. Let X equal the total population of frogs in the whole pond. So that's the thing we're looking for. We know that there are 75 tagged out of X. So if we're thinking about the whole pond, right? So here's the whole pond. We've tagged 75, and we don't know how many are in the whole pond, X. Then we're going to take a second sample on another day, and we found that 7 out of 50 had tags. That's 7 out of 50. That's its own fraction. So the sample was 75 out of some unknown total population. And then the second one was 7 out of 50. So we can make a prediction. We can cross multiply 7 times X and 75 times 50 and get that X is approximately 536. So we would say we tagged 75 and we're predicting we think there's 536 in the population because that's the same ratio as our second sample, which was 7 out of 50. After another week passes, the biologist captures 60 frogs and notes that 8 are tagged. So captures 60 frogs and notes that 8 are tagged. Estimate the frog population based on the new sample. Remember, she originally captured and tagged 75. So we do this in a short amount of time, so we really aren't taking into account frogs dying and frogs being born. So we're assuming that because the time frame is pretty small, that we don't have a lot of that kind of change. So we're going to use the original 75 tagged. So we would say there are 75 tagged out of the population that we don't know, right? That's our yellow fraction. That's our original. And then we're going to say in our new sample, 8 had tags out of 60. So we would cross multiply 75 times 60 has to equal 8 times X. That's 4,500 equals 8X. Divide both sides by 8. We get 562.5 equals X. So we would say based on this sample, we think there's about 563 frogs in the pond. Let's try a different one. If you were able to combine the 2 samples, 8 out of 60 with 7 out of 50 for one large sample of 110 frogs, what estimate does this sample give you for the size, of the frog population? So we would say 8 out of 60 and 7 out of 50. That is 15 out of the 110 that we sampled total. And the original was still, we tagged 75 out of the whole population. So we've still got that same 75 out of X. If we combine our samples, we have total tagged, recaptured 15 that had tags out of 110 that we attempted to check. So we would say 15 times X equals 75 times 110. And that's 8,250. Divide both sides by 15. When I put the samples together, I get that X equals 550. So we're going to say about 550 frogs in the pond. Now that kind of makes sense, right? This one was 536. This one was 563. 550 is kind of in the middle. It's sort of like an average, but not quite. I didn't add them together and divide by 2. Reason for that, this sample had 60 and the first sample had 50. So the sample sizes were not the same. So I can't just add the 536 and the 563 together and divide by 2. Combining them and pretending they're sort of one large sample makes it a little bit more fair since one of the samples was bigger. All right. In the survey by Mr. McQueen, 6 out of 14 eighth graders said their favorite project was creating the bobbleheads. If there are 88 students in the 8th grade, how many could you predict would say bobbleheads were their favorite? So we had 6 out of 14 8th graders. Like we took that as like our actual survey. We know that there is a total population of 88 students. So we're trying to find how many out of the population 88 if our sample said 6 out of 14. So 88 is our total population, and we're trying to predict that population's group. Like if we were to have interviewed all 88, how many would say bobbleheads, considering our little sample came up with 6 out of 14? So if we do 14 times x equals 88 times 6, we're going to get 14x equals 528. Divide both sides by 14, and we're going to have x is approximately 37.7. And since we can't have 37.7 students, we would say about 38 students liked bobbleheads best. Now, it might not be 38 in practice, right? It might be 40, it might be 35, but it's probably somewhere right around there. We only surveyed 8th graders because we were only interested in how 8th graders felt about the project. Now, if we had 7th and 8th graders doing bobbleheads, then we might want to interview 7th and 8th graders to find out how 7th and 8th graders felt. A container of ping pong balls is on display for a contest held in a local mall. There are 50 ping pong balls marked with a small X to show you are a winner. Every person who enters the mall gets to pull out one ping pong ball. Of the first 350 people to enter the mall, only 7 have won. So there's our sample of 350 people who entered the mall, only 7 have won. And we know that in the big container that there are 50 marked with an X. Estimate the number of ping pong balls in the container. So we're saying we marked 50 out of some larger unknown amount. So that's our setup. That's like what was in the original container. And then we've done a sample, the one in pink. Only 7 have won out of 350. That's how we set this up. What's the setup? What's in the original box? 50 out of some really large population. And we've taken a sample where the first 350 people have entered and only 7 have won. So if we cross multiply 7x equals 50 times 350, we would have 7x equals 17,500 and divide both sides by 7. We are going to estimate that there are 2,500 ping pong balls in the container. So we estimate 2,500 total ping pong balls in the container. All right. I like the next question because this kind of stuff fascinates me. I love watching television shows about this kind of stuff. A pretzel manufacturer samples 100 bags of pretzels and finds that 3 are underweight. So samples 100 bags and finds that 3 are underweight. So if the bag says it's got to have 6 ounces of pretzels, it's got to have 6 ounces of pretzels. If it says that it has 20 ounces of pretzels, it has to have 20 ounces. Over is fine, but under is not. You cannot do that. So the company manufactures 20,000 bags each week. Approximately how many are underweight? So what's the setup? What's the big picture? We want to find how many are actually underweight out of the 20,000 total that they manufacture in a week. And then we took a sample that 3 are underweight out of the 100 we looked at. This is not going to go well. So 100 times x equals 3 times 20,000. So 100x equals 60,000. And when I divide both sides by 100, we're going to find out that x is 600. That's a lot. About 600 underweight bags each week. And that means those should not be being sold. People can actually, and have actually in the past, filed like class action lawsuits and sued companies and stuff over things being labeled incorrectly. So you would want to make sure that you weren't putting a product out that was underweight. Those bags need to be pulled off the shelves or not sent out to begin with. And those bags often get donated because it does not really help companies to try to do something with them. Usually they end up donating them to food shelves and stuff like that. A factory produced 20,000 shirts. 1,500 of them were returned because there was a problem with the stitching. The company who sold the shirts realized that they were not doing any sampling to ensure the quality of the clothing. If they had checked 600 shirts, how many would they have found to be defective? Now, what's interesting in this case is that we actually have the population, right? 20,000 shirts. And we know that out of 20,000, 1,500 of them got returned. That's our setup. If somebody had been checking and they had checked 600, how many of the checked shirts would they have found had a problem with the stitching? So this time we're sort of finding something on the other side of the proportion. So 20,000 times X equals 1,500 times 600. So 20,000 X equals 900,000. And we would divide both sides by 20,000 and get that X equaled 45 defective shirts. And that would have just been in the sample. That would have raised some eyebrows. Like in the factory, if they had found 45 shirts to be defective out of 600, somebody would have gone, whoa, 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 we need to fix this before we produce 20,000. That's why companies do sampling. If a sample found that 18 shirts, if the sample found 18 shirts to be defective, how many were in the sample? So again, we're going to use that same 1,500 out of 20,000 had defects. If the sample found 18 shirts to be defective, how many were in the sample? So 18 defective out of the whole sample. That's a tricky one to set up. We're saying 18 are defective, defective numbers go on top, total numbers go on bottom. So we would do 20,000 times 18 equals 1,500 times X. This number going to be 360,000 and divide both sides by 1,500. It would be 240. So in order to get 18 defective, there would have had to have been 240 in the sample. Or about 240, because it might not have been that you caught all of them, or you might have had one batch that was really heavy on defects. But overall, this whole thing about predicting is saying, like, what do we know to be true for the whole compared to what do we know to be true for the sample?